All right, this is the second short video for this evening, and I wanted to talk about stochastic matrices. This is the official word, and this means probability matrices. So we want to look at probability matrices, and I think the easiest way to introduce this is to simply do an example, because this is how they work. So here's my example. Northfield, Minnesota, 1978 maybe. You are there. So most TV at that time didn't have cable, didn't have satellite, just used the airwaves, and so there were TV stations. And I'll call this nothing special, or N, for no additional TV. And there were about 15,000 people that had this situation. But cable was coming in, so there were some folks with cable. And I think, let's see, I think about 500 people had cable. And there were a few people with satellite. And I think it was about 100 people with satellite. So this is where we're going to start. But then at the end of the year, or by the end of the year, there'd been sort of a change. About, let's see the figures here, about 85%, 85% of the people that were in the no special category, nothing special, they did not change. But the other 15% did change, and 5% of them came here and took cable, and 10% of them became satellite users. And we also had changes from cable. So about 80% of the cable folks stayed at cable, 0.8, and about 10% quit and became nothing special again, like they were before, and about 10% became satellite users. Now notice that these are percentages, so the 80%, the 10 and the 10 have to add up to 100. There's no additional information there. You might say, well, what about the people that moved out and the people that moved in? Well, yes, we're working with a sort of a simple idea here, but you can build on that idea to get more complicated things. So let's start with this one, which is fairly straightforward. And I need one more color. Maybe I have blue, I have a different green. So the satellite folks, let's see, 90% of them, 0.9, remained satellite folks. 5% became cable, and 5% became nothing special, no subscription. Now, this information can be recorded in a matrix. It's a lot of information, but we can make a 3x3 matrix where we describe this. So let's label it this way. Cable, satellite, nothing special. And we'll look at the cable folks. And the cable folks, 85% of them remained cable folks. 10% of them became satellite, and 10% of them became no subscriptions. Moving on, for the satellite folks, 90% of them remain satellite. Satellite to satellite is 0.9. Satellite to cable is 0.05. And satellite to nothing special, no subscription, 0.05. And the no subscription service, let's see, 85% of them stayed there. And how many became satellite? 0.1 became satellite, 10% of them. And 5% of them became cable. So this is the probability matrix. This is a stochastic matrix. And you can check because these numbers are all non-negative and they add up to 1 in every column. So that's what it takes to be a stochastic matrix. Double stochastic would mean that the rows also add up to 1. These do not. But here's our situation. Now I'm going to show my screen to you and we'll take a look at how we deal with this. There's my Mathematica. So in this Mathematica here, I have entered the information. The matrix M is 0.8, 0.05, 0.05. So that's this first row. Hopefully I have this. And then I'm going to ask for the matrix form of that. And then the initial group is in the cable, we had 500. And in satellite, we had 100. This is the famous R0 that they use for all initial conditions. They're using it for COVID now. Maybe you've seen R0. And so let's enter that and see what we got. Okay, so this is just this information. Let's see what M times R0 is. So this represents what happens, the transition after a year. And I want to look at the matrix form of that. And then let's take that cell and make it a little bigger, maybe. So we started with R0, which was 500, 100, 1,500, 15,000. And at the end of the first year, the subscriptions look substantially different. Instead of 500, we have 1,155 cable subscribers. And instead of 100, we have 1,640 satellite subscribers. Notice that that's largely due to the fact that 10% of the non-subscribers became satellite users. So what would we get if we did a second year? Multiplying by M is like iterating year after year. So after 1 year, it's M times R0. After 2 years, it would be M times that. So let's see what we get. Uh-oh. Let's try again. So now we see a big move out of the no subscription. We started with 15,000. Now we're just about at 1,500. So it's diminished by an enormous amount. Something maybe you wouldn't have expected with 85% of the people continuing each time. And we have, or those are the cable subscribers. For the no subscription, we have 11,000 from 15,000, a big decrease. So this is after just 2 years. What would happen after like 10 years? Well, there is a way to do some of this that's a little different than what we have. It's called matrix power. So if we take the matrix power of M, and let's say we just do 2 years, so this should match up with what we have above. So I will actually look at then the matrix form of that. Matrix form of matrix power of M2. So it should have given it to me, but I don't see it. Maybe. I have an error here, but I'm not sure exactly what it is. Let's get off this matrix form and just look at the matrix power. So when we just look at the matrix power of M2 with R0, we get the same thing, 1646.25, that quarter of a person, 2872 and 11,081.7. So this is the subscriptions at the end of 2 years. We could continue doing M.M.M, but I could use this matrix power thing and do like the 20th power. And we would get this. Now, something interesting happens here, so pay attention. This is, well, you can pay attention or not, but this is the 20th power of M times R0. So this is what happens after 20 years, or 1998. Let's take a look at what would happen after 200 years. Now, keep these numbers in mind. They're going to change. We had 3,111 before. Now we had 3,120, so there's very little change between the 20th year and the 200th year. We could try the 2000th year. And no change. So things stabilize. These probability matrices have the property that after a while, they stabilize and don't change. Now, by the 20th year, they hadn't stabilized yet. It's the 3,120 that stabilizes them. We could see if it's stabilized by the 30th year. Not quite. 3,120 is what it takes, so maybe the 35th year. Not quite, but essentially it has. And after the 40th year, after the 100th year, oops, that was 1,000th. Okay, so there after the 100th year, it's stabilized. So powers of these matrices will powers of stochastic matrices stabilize after a certain number of years, and this is called the steady state behavior. You have big initial changes, but then after some time, they stabilize. What they stabilize to is important, and how long it takes is important. And I'll give you some problems for homework dealing with these stochastic matrices and setting up these matrices and finding out where they stabilize tomorrow. So thanks a lot. See you then.